Welcome, deep divers. Many of you know your way around the cosmos, but today we're diving into something truly mind-bending. Wormholes. You see them in sci-fi all the time, but they actually have some, well, pretty deep roots in real physics. Just like try for a second to imagine the scale of our universe. It's just unbelievably huge. Really makes your head spin. Now, picture this. Our telescopes spot a perfect Earth-like planet way off in another galaxy. Amazing, yeah.
Incredible potential, definitely.
But then, the reality check hits. Even with our fastest ships, like the ones going maybe 28,000 kilometers an hour, reaching Andromeda, our closest big neighbor galaxy that's 2.5 million light years off, would take something like 94.5 billion years.
Billion with a B.
Yeah, billions. And even if we magically hit light speed tomorrow, still 2.5 million years. Guess I'll stick to watching Netflix in this galaxy for now then.
Yeah. It does sort of burst the bubble of cosmic wanderlust, doesn't it? Those distances. They mean that for one person in one lifetime leaving the Milky Way, let alone exploring other galaxies, it just feels impossible.
Totally. What's the point of finding these amazing places if we can never, ever get there?
Well, that's the kind of question that really gets theoretical physicists going. Because what if space itself, the fabric of it, had a kind of cheat code?
A cheat code. I like the sound of
A
that.
theoretical shortcut, yeah. Something that could, slash millions of light years down to maybe months or even minutes.
Okay, now you're talking. That's the wormhole idea, right? Like in the movie Interstellar.
Exactly.
Yeah.
They find that wormhole near Saturn, zip through it to another galaxy. It's key to the whole story.
And you're saying that's not just Hollywood fantasy?
Well, the idea behind it isn't pure fantasy, no. It's actually grounded in some very real, very strange science.
Okay, interesting.
And that's really our mission for this deep dive. We want to unpack what wormholes actually are, theoretically speaking, how they connect to the very fabric of the universe, and look at the surprising science behind it all, based on the sources you share.
Right. So where do we even start? How do you get to the idea of a shortcut through space?
Well, like a lot of the universe's biggest secrets, it really starts with Albert Einstein. His theory of relativity. That's the foundation for all of this.
Ah, Einstein. Of course. Knew he'd show up.
He has to. It comes down to his field equations. He presented them publicly back on November 25th, 1915, to the Prussian Academy of Sciences in Berlin.
The field equations.
Right.
I've seen them written as one elegant line, but I hear that's deceivingly simple.
Oh, incredibly deceiving. It's actually a complex set of 10 non-linear partial differential equations. The full form is...
Oh, yeah. It's intense.
Okay, skipping the math test then. So, in, plain English, what do these super complex equations tell us? What's the big idea?
Basically, they describe how matter and energy warp space-time. Einstein showed us space-time isn't just empty stage, It's dynamic.
Like the classic analogy, the stretchy rubber sheet.
Exactly that one. Imagine a big mesh, you put heavy stuff on it, like bowling balls for planets and stars, and the mesh bends and curves.
Yeah. That bending is gravity. That's how mass distorts space-time. The more massive the object, the bigger the dent, the stronger the gravity.
So space-time itself can be warped. Wow. Okay. And Einstein figures this out, writes the equations. Did he solve them himself? Find all the answers?
Surprisingly, no, not completely. Einstein himself only found an approximate solution for a specific sort of simplified case.
Really?
Yeah. The first person to find an exact solution was Carl Schwarzschild. Just a year later, in 1916, he worked out precisely how space-time curves around a single, non-rotating ball of mass.
Schwarzschild. Okay, and what did his solution reveal?
Well, it led directly to the concept of singularities. These are points where the curvature of space-time becomes, well, infinite. It essentially breaks.
Infinite curvature.
Yeah, a point of infinite density where the known laws of physics just stop working. And that theoretical prediction, that was basically the mathematical proof for black holes, almost a century before we actually saw one with the Event Horizon Telescope in 2019.
Amazing. So black holes came out of solving Einstein's equations, but you said a solution, implying there might be others.
Exactly. Think about a simple math equation, like a quadratic one. Sometimes you get two valid answers, right? X could be 2 or X could be 3.
Yeah, okay.
Well, Einstein's field equations are vastly more complex, but the same principle applies. They can have multiple, different, but equally valid mathematical solutions. Black holes are one type of solution.
And wormholes are another.
Precisely. It suggests the universe, governed by these equations, might allow for things far stranger than just black holes, things like these theoretical shortcuts. This other solution is technically called an Einstein-Rosen bridge.
Einstein-Rosen bridge. Okay, who figured that one out?
That was Einstein again, working with his assistant Nathan Rosen back in 1935. They found this solution together.
So Einstein himself co-discovered the wormhole solution. Cool. Okay, how do we, picture this? How does this shortcut actually work? I've heard the paper analogy.
That's the classic one, yeah. It's simple but really effective. Imagine you have a flat piece of paper, mark two spots on it, A and B, pretty far apart.
Okay, got
The
it.
quickest way between A and B on the flat paper is a straight line, right?
Right.
But now, what if you could lift that 2D paper up and bend it through the third dimension? You could fold it so point A is right over point B.
Okay, so they're almost touching, but in 3D space.
Exactly. Now, the shortest path isn't that long line across the paper anymore. It's tiny jump, maybe punching a little hole straight through the folded paper from A to B. That's the wormhole concept.
So applying that to us, we live in 3D space. The idea is our 3D space could be bent or folded through some hypothetical fourth dimension.
That's the theoretical leap, yes.
Mhm.
If our space could curve in a higher dimension, then a shortcut, an Einstein-Rosen bridge, could potentially link two very distant points, like, say, our galaxy and Andromeda.
Whoa. It's hard to visualize bending our whole universe.
It is, because we can't perceive a fourth spatial dimension. But think about it like this. Flying from Delhi to New York, on a flat 2D map, the straightest looking line goes kind of over Africa, right?
Yeah, seems logical on a map.
But look at a 3D globe. The actual shortest flight path goes way up north, over the Arctic, Finland, Greenland, that way.
Right, the Great Circle route. Looks curved on the flat map, but it's shorter.
Exactly. It's the shortest path in 3D, even though it looks longer or weirder in 2D. So maybe the shortest path between galaxies isn't a straight line through our 3D space, but a shortcut through a higher dimension.
That actually helps. Okay.
Yeah.
And the name wormhole, where did that come from? It's so descriptive.
That term was coined much later, actually, by physicist John Wheeler in 1957. He was writing about these Einstein-Rosen bridges.
And he used the worm idea.
Yeah, the analogy he used was a worm on the surface of an apple. Does it crawl all the way around the skin to get to the other side?
Mhm.
Or does it just chew a hole, a tunnel, straight through the apple?
A wormhole. Clever.
It captures that shortcut idea perfectly.
Okay, so if they exist, these theoretical tunnels, what would one look like if we stumbled upon one? Not just like a hole in space.
Probably not, no. The theory suggests it would likely appear as a sphere, like a crystal ball, maybe.
A sphere. Okay. And looking into it.
You'd see a really distorted, curved view of the region on the other side, like looking through an extreme fisheye lens. Distant things, maybe the Earth or stars on the far end, would look warped, kind of circular, and seem to recede away into the center.
Huh. So like the visuals in Interstellar.
Actually, yeah. Scientists who consulted on that film said the depiction was surprisingly accurate based on the theoretical models. It wouldn't be a tunnel, you see, but a sphere showing a warped view of the destination.
It's, yeah, tricky to imagine holding that image. But let's just stress this again. This is all still theory, right? We've never actually seen one.
Absolutely. It's a mathematically valid possibility within Einstein's framework, but zero observational evidence so far. Purely theoretical at this point.
Okay. So if they exist, we hit some big practical hurdles. Like, first off, how do you even keep one open?
Yeah.
And then, where does it go?
Yeah, those are the killer questions. To keep a wormhole's mouth open, theory suggests you'd need something with absolutely immense gravity.
Like what?
Well, according to Einstein and Rosen's original idea, only black holes would have enough gravitational pull to potentially open and sustain one end of this tunnel. The gravity would pull things in.
Okay, so one end is a black hole. But wait, that leads to the next problem, right? If the other end is also a black hole, what good is that?
Exactly. That's the trap. If it's black hole to black hole, you fall on one side, and
Right.
well, you're just trapped in another black hole. Not exactly a useful transport system.
Right, it's a cosmic dead end, not a highway. So you need something else for the exit, something different.
Precisely. You need an exit door, not another entrance trap. And this is where another really strange theoretical object comes into play. The white hole.
White holes, okay, never heard of those as much.
Mhm.
Are they also a solution to Einstein's equations?
Yes, they are. Just like black holes and wormholes, white holes pop out is another mathematically possible solution. And they are essentially hypothesized to be the exact opposite of black holes.
Opposite how? Black holes suck things in, nothing escapes.
So white holes would do the reverse. Nothing could enter a white hole from the outside. Things could only come out.
Only come out, so they'd be spewing stuff like.
Theoretically, yes. Light and matter could exit, which means they'd likely be incredibly bright, maybe blindingly white, hence the name.
Who came up with white hole?
That term was coined by a Russian theoretical physicist, Igor Novikov, back in 1964.
So it's like time-reversed black hole.
In a way, yeah. A black hole's event horizon is the point of no return, cross it, and you can't get out. A white hole's event horizon would be a boundary of no admission. You can't get in from the outside. Things inside could see and interact with the outside universe, but nothing from our side could cross inwards.
Okay, that's weird. Black holes inhale, white holes exhale. But how would a white hole even form? We know black holes come from massive stars collapsing. What about white holes? Is there a theory?
That's where it gets really speculative and debated. Unlike black holes, there's no widely accepted mechanism for how a white hole might form naturally.
Oh,
Yeah. I mean, there are ideas. One fringe idea is that maybe the Big Bang itself was a kind of giant white hole event, the ultimate spewing out of everything.
huh. Okay. Any other ideas?
Another more recent thought connects to Stephen Hawking's work on black hole evaporation. Hawking showed that black holes aren't perfectly black. They should slowly leak radiation over vast timescales and eventually maybe disappear.
Hawking radiation.
Right. So the question is, when a black hole dies, what happens to all the information and matter that fell into it? Quantum mechanics has this fundamental rule, sometimes called the no-hiding theorem, that says information can't truly be destroyed in the universe.
It has to go somewhere.
It has to go somewhere. So some theorists speculate that maybe, just maybe, as a black hole evaporates and dies, all the stuff it swallowed gets, well, spat back out, perhaps through a white hole that forms at the very end. It's a way to conserve that information.
Wow, like a cosmic recycling program. Black hole eats, white hole spits it back out eventually. That sounds almost neat, but I feel a but coming.
There's always a but in theoretical physics, and it's a big one. Many scientists argue white holes are flat out impossible.
Why? Because they're just too weird.
Not just weirdness, it's about a fundamental law of physics. The second law of thermodynamics.
Oh boy, entropy.
Entropy, yeah. The law basically says that the total disorder, or entropy, in a closed system can never decrease. It always stays the same, or, more usually, increases.
Okay, and black holes?
Black holes fit this perfectly. They gobble up organized matter and energy and shred it, increasing the overall entropy of the universe. They're messy eaters.
Makes sense. So white holes would.
White holes, by spewing out matter and radiation, would seemingly decrease entropy locally. They'd be creating order from, well, wherever this stuff comes from. And that appears to violate the second law. That's a major, major roadblock for the white hole idea. It would break a fundamental rule.
That does sound pretty damning. But was there ever anything spotted out in space that made people think, hang on, maybe?
There was one really weird event, yeah, it's still debated, GRB 060614. It was a gamma-ray burst detected by the Swift Observatory on June 14, 2006.
A gamma-ray burst. Aren't those usually linked to black holes or neutron stars?
Usually, yes. Typically, they happen when a massive star collapses into a black hole or neutron stars merge. You expect to see the signature of the star of the merger. But this burst, GRB 060614, was this huge flash of gamma rays and light that just appeared and then vanished. And crucially, astronomers couldn't find any trace of a supernova or a host galaxy where you'd expect it to originate if it were a typical GRB from a collapsing star.
No star, no galaxy, just boom.
Pretty much. Just this massive orphan burst of energy, which led some scientists to tentatively, very tentatively speculate. Could that have been a white hole spontaneously appearing and releasing energy?
Whoa.
But it's a massive if. No other event quite like it has been convincingly observed since. So it remains a tantalizing mystery, not proof.
So white holes and space-time wormholes are still very much on the drawing board, theoretically speaking.
Very much so. Fascinating mathematical possibilities, but firmly in the realm of theory for now.
Okay, but shifting gears slightly, wasn't there some kind of wormhole created in a lab recently? Not bending space-time, but something else?
Ah, yes. That was a really cool development in 2015. Scientists managed to create what they called a magnetic wormhole.
Magnetic wormhole? What does that mean?
Right, so it's important to stress this didn't involve bending space-time or gravity at all. What they did was manipulate magnetic fields.
How? I thought magnets always have a north and south pole, right? You can't separate them.
Normally, no. If you cut a bar magnet in half, you just get two smaller magnets, each with its own north and south. But these researchers use special materials, things like metamaterials and superconductors, specifically yttrium barium copper oxide, cooled way down with liquid nitrogen.
Oh, okay, fancy stuff.
Very fancy stuff. And they built a device, a sphere, that could effectively channel a magnetic field from a source outside the sphere, make it travel through the sphere as if it were invisible to the field, and have it emerge out the other side, appearing like an isolated magnetic pole, a monopole.
So the field went in one point and out another, like it tunneled?
Exactly. The magnetic field lines entered one side, disappeared inside the device, and reappeared on the other side, effectively creating an invisible tunnel or shortcut for the magnetic field. So while it's not a spacetime wormhole, it demonstrated the principle of creating a topological wormhole for a different kind of field. Really ingenious.
That is clever. Shows how even theoretical ideas about space-time can inspire real, tangible tech in other areas. Are there other non-wormhole ideas for faster-than-light travel that also come from Einstein's equations?
Yes, definitely. The wormhole isn't the only theoretical loophole people have found. Another famous one is the Alcubierre Drive.
Alcubierre Drive. Sounds familiar.
It was proposed by Miguel Alcubierre, a Mexican theoretical physicist, in 1994. The idea isn't that the ship itself travels faster than light through space. Instead, the ship creates a bubble around itself,
A bubble?
a warp bubble. It would theoretically work by contracting space-time in front of the bubble and expanding space-time behind it. So the ship inside the bubble stays still relative to its local space. But the bubble itself gets pushed along, potentially faster than light, by warping space itself.
So you're surfing on a wave of space-time.
Kind of, yeah. You're moving space around the ship rather than moving the ship through space. Again, purely theoretical. Needs exotic matter with negative mass, which we don't know exists, but it's another valid mathematical solution that pops out of Einstein's framework.
Wow. So Einstein's equations just keep on giving, revealing these bizarre possibilities. Okay, we've covered a lot. Mind-bending distances, space-time fabrics, black holes, white holes, wormholes, both cosmic and magnetic. What's the big takeaway here?
Well, I think it's a really powerful reminder, isn't it? That concepts like space-time wormholes and white holes, as purely theoretical as they seem now,
Yeah.
we have to remember that black holes were also just a weird theoretical prediction from these exact same equations for decades. They seemed impossible, just math on paper, until technology and observation caught up and proved they were real.
That's a great point. What's theory today could be observation tomorrow.
Possibly. Or maybe these specific concepts won't pan out. But the ongoing exploration of Einstein's equations, trying to understand all their implications, is guaranteed to keep revealing deeper, more fascinating insights into how our universe actually works. The journey itself is valuable.
Absolutely. The quest continues.
Indeed. And it leaves you wondering, doesn't it? Given the absolutely wild ideas that have already emerged from physics in the last 100 years or so, things our ancestors couldn't even dream of, like black holes swallowing stars, or the possibility of cosmic tunnels, what other, even stranger solutions or phenomena might still be hiding, coded into the math, waiting for us to find them or figure out how to look for them?
What else is lurking in the fabric of space-time? A truly provocative thought to end on.